Hello, and welcome to Aggressive Physics. Today is day 116, and what I'd like to do today is a couple of sample problems. We've already discussed the fact that current can flow when there's a closed circuit, which is a redundant term, a complete path, when it flows through a metal typically because of the sea of electron models, and because it has a push. We also discussed the fact that current will flow as a volume rate of time. So it's the amount of charge that passes a given point in a given time in a circuit. And the equation is I equals Q over T for that. We then discussed resistance and the fact that resistance is based on the material that's used and the geometry of that material, the length and the cross-sectional area. We also discussed the fact that the resistance equation is R equal PLA, rho L over A. Now, those are all based on the fact that there's a temperature that's constant. The temperature of 20 degrees Celsius is what we have for our chart in the reference table. But you can have resistivity values for materials at different temperatures. But typically we stick to room temperature because that's the temperature that will work in the lab, and that's the temperature that we'll have around our house. Of course, if you have extreme climate conditions, you could have much higher or much lower temperatures than around 70 degrees Fahrenheit. But we stick to 20 degrees Celsius, and you could always look at a new value if you have a colder or a warmer environment. Now today what I'd like to do is some sample problems dealing with R equal PLA. So we're going to take out the whiteboard and we're just going to do some sample problems. We'll call this a work day. And once we get R equal PLA under our belt, what we'll do is look at Ohm's law. And we'll start talking about that tomorrow. Thank you. All right. Well, now that we have the equation to find resistance, which is R equal PLA, what I was thinking is we could find the resistance on a standard gold bar. So I looked up to the dimensions, and they're, of course, in inches. 7 inches by 3 5/8 by 1 3/4. So the first order of business is to convert to centimeters. Now 1 inch is 2.54 centimeters. So let's get rid of the inches by multiplying each of these by 2.54. And of course, the symbol, the quotation symbol, is the symbol for inches. So 7 times 2.54 gets us 17.78. So I'm going to start there. 17.78 centimeters. 5/8 is 0.625, so 3.625 times 2.54 gets us 9.2075. 9.2075 centimeters. And then 1 3/4, so 1.75 times 2.54 is 4.445 for this one. 4.445 centimeters. Now, if we look at connecting the gold bar to a circuit from the endpoints, that would mean the cross section is this part right here. So the cross section is going to be based on the base and height of that rectangle. So it's going to be 0.092075, because I'm going to convert that two places to make it meters. So that's meters, times 0.04445. And the value in square meters for the area is base times height, which is 0.00409 meters squared. Now the length, that's 17.78 centimeters, so I'm going to put 0.1778 meters over 0.00409 meters squared. So that's L, that's A, and all I need to know is the rho, which is the resistivity. Now the resistivity is on my chart, and gold is listed as 2.44 times 10 to the negative 8 ohm meters. Now these are all listed at 20 degrees Celsius, and that's because the resistance of a material is based on room temperature, at least these values for resistivity. This value will change as the temperature changes. In fact, resistivity will go up as the temperature goes up. So there's a direct relationship between the resistivity and the temperature. And that's because as the average kinetic energy of the molecules start to vibrate more rapidly, it's going to be harder for the electrons to flow. So at this point, I just need to find the resistance. I'm going to multiply 0.1778 times 2.44 e negative 8. And I'm going to divide that by 0.00409. Now, the resistance of a gold bar from the endpoints is 1.06 times 10 to the negative 6, and the unit is the omega. Now, what I can do is simplify this and get rid of the 10 to the negative 6, and the resistance would be 1.06 microohms. And that just sounds cooler already, microohms. So the gold bar connected end to end has a resistance of 1.06 microohms. Okay, now what I found in my basement was a spool of speaker wire that I have used over the years to wire up speakers for my sound systems. And I've changed the location of my speakers both inside and outside my house. And most of the time when I'm doing indoor wiring, I'm going to use speaker wire like this. There's two sections, and that connects to the two terminals, typically of the old speakers that I would use. And this is listed as AWG, which is American Wire Gauge 24. So speaker wire that I have is 24 gauge. So it's AWG, American Wire Gauge 24. And what the wire gauge means is that the bigger the number, the smaller the wire. So you can have everything from 000 up to around 30, I think. But in this case, 24 is fairly thin wire. And I looked it up. There's a standard for this. And the diameter is 0.511 millimeters. Now, if we think about this, the wire that I'm using here is cylindrical, and it's small. It's hard to see on this video because of the size of the wire, but that represents a cross section that's circular. So you're going to do pi r squared for the area. Now, 0.511 millimeters is the diameter, so I have to divide that by 2. So 0.511 divided by 2 is 0.2555, so 0.2555 millimeters is the radius. And I'm going to make that 10 to the negative 3 to get rid of the milli. So the area of this wire is pi times 0.2555 times 10 to the negative 3 meters. And I'm going to square it. So that number squared, 0.2555 e negative 3 squared times 3.14 gets me the area, cross-sectional area, is 2.05 times 10 to the negative 7 square meters. Small value, but the diameter is small, and that was small for millimeters. Now this is copper wire, so the resistivity for copper, I'm going to look on my chart, is 1.72 times 10 to the negative 8 ohm meters. And then finally, the length that I bought was 75 feet. Now, fortunately, it said right on the spool, that's 22.8 meters, but I could have easily converted that with 3.28 feet per meter. Now, the equation is R equal plah, and assuming we're at room temperature, I can multiply rho times the length and divide it by the cross-sectional area. So I'm just going to do that now. 1.72 e negative 8 times 22.8, and that's going to be divided by, and I already have the area, 2.05 e negative 7. So the value for the resistance of the entire spool of wire is 1.91 ohms. Now, with that said, that's for one of the pieces of wire. So since there's two strands, you could multiply that by 2 to find the total resistance of the entire spool if you unhooked it and connected it together. But since that's going to be difficult to do, typically this would be the value of one of the pieces of wire. But if you just multiply by 2, the total resistance is 3.82 ohms for the total spool. And we'll say both strands of wire. So you need to look up a few things. We had to convert a number or two, watch out for diameter, and finally resistivity is going to be listed in a chart. And our chart has 6 common values, and if those aren't ones that you're looking for, you'll have to look it up on a different chart. All right, let's just look at one more resistance problem with wiring. I found in my basement a component that we took out. This was a dimmer switch that we had in our dining room when we remodeled. We took out the dimmer switch and put in a regular on-off switch. And some of the wiring we had to change was this 14 gauge wiring that's typical for household wiring projects. Now this has 3 wires in it, and it's 14 gauge wire, and that will allow 15 amps of current to flow quite safely through the wires. Now you notice there's 3 parts because you have a positive and negative terminal, and then this one that's bare, that's going to be your ground wire. And the ground wire is important because you'll connect that to, ultimately in each house there should be a grounded wire, usually in the basement, that's then connected to the earth, and then any overload in the circuit can flow through that instead of electrocuting someone in the house. But what I had to do is I had to look up the diameter of a 14 gauge wire, and it said it was 1.628 millimeters, and that's the diameter. Now, like a standard wire, it's cylindrical, so the cross section is going to be a circle, so the area is pi r squared. So I'm going to have to divide the diameter by 2 and then convert to meters and then square it. So 1.628 divided by 2 is 0.814 times 10 to the negative 3 meters, and that's going to be the radius. That's the number I'm going to plug into the r squared. So it's 3.14 times 0.814 e negative 3 squared. And I get for the cross-sectional area 2.08 times 10 to the negative 6 square meters. Very small value. Now my R equal PLA equation. The resistivity is based on copper. This is copper wiring. I'm not rich enough to wire my house in gold. I was thinking about, after we did the gold bar problem, if you actually could wire a house with gold, that would be quite expensive. We could do a problem on that later on. 1.72 10 to the negative 8 ohm meters is the resistivity, and that's assuming we are at room temperature. L, let's just do, for this problem, I don't remember how big the roll was that I purchased, but let's just assume it's the same as the speaker wire so we can compare. 22.8 meters, and the cross-sectional area is 2.08 times 10 to the negative 6 square meters. Now, if you notice, these meters on the top will cancel the meters on the bottom, and you'll be left with ohms. So, mathematically, it's a fairly simple process at this point. The difficulty in physics is usually setting up the problem, not plugging the numbers in. So I'm doing 1.72 10 to the negative 8 times 22.8, and dividing that quantity by 2.08 e negative 6. And I'm getting the resistance. Oh, I don't know why I put a vector symbol over. I thought of resultant. Is 0.189 ohms. Now, if you remember, the speaker wire had a bigger value. It was 1.8 or 1.9 ohms. This is much smaller. Now, because it's made of the same material, the row is the same. The length we had was the same. But remember, the cross-sectional area for this is much larger. Bigger cross-sectional area, smaller resistance, because the electrons have more room to flow and less obstacles as they travel. So there's an indirect relationship between the resistance and the cross-sectional area. So as the wire gauge goes down, that would mean the diameter goes up, and as the diameter goes up, the resistance goes down as well. So you could look at relationships between variables as well. But those are a couple of examples of R equal PLA, and from here we'll move on to different equations. Thank you.